for time. So time is equal to distance divided by rate. So on the way back, how much distance did she cover on the way back? It's not a trick question.
Um, yeah, man, now I'm thinking of it as a trick question.
It's not. It's not. You go out somewhere and you come back. Distance back is the same as the distance there.
So basically, like,
How far did she go uphill?
well, this says 5 miles.
Okay, so it's 5. And then what was her rate on the way back down the hill?
Um, 15 miles per hour.
There you go. So that's the answer is 1/3 hours, but we would want to convert that to minutes. What is a third of an hour?
A third of an hour. I have no idea.
Yes, you do. How many minutes are in an hour?
60,
Okay, what's a third of 60?
30?
Try again.
Wait,
That's
that's
half.
half of 60.
Yeah,
Um, if it's okay, if it, I was about to say 40.
that's 2/3 of an hour.
Okay, we're getting somewhere.
Do you have a calculator?
Yeah,
Okay, take 60 and multiply it by a third or divide by 3.
60 divided by 3, 20. That will
20
be my
minutes.
next guess.
There you go, 20 minutes. All right. Okay, so what is the total time traveled? Okay, so the total time is the time up plus the time down. How much time did she take to go up and down? In minutes.
It took her, so it's 20 minutes for the way down. It was 30 minutes on the way up,
Okay,
so 50 minutes.
right. Very good. And then the total distance,
The total distance was, so it says 5 miles, but I don't think that's right.
well, you have the distance there and the distance back.
So like 10.
Yeah, 5 plus 5 or 10 miles. Okay. All right. Now these graphs here are a little bit harder. We're actually going to go do we'll try and do 6 first and then come back to um we'll try and talk about what these are. So let me see which one makes more sense to do. Okay. So this graph is showing you position versus time. So here the position, like think of the position here as being like 10 meters away from your house. Like, that's maybe 100 meters. I don't know. And then you get down here, you're 0 meters from your house. So can you think of a scenario where you start, some distance away from your house and then you get back to your house?
Yeah, like let's just say well, okay, let's say I'm at the mailbox area at my gated community and I walk back to the house basically.
That's
Like
correct. Now, what do you notice about this graph here, the slope? Is it the same slope
it's a
or not?
different slope. The slope's a little bit tilted.
So the slope is actually constant here, which means that you're not running You're not stopping anywhere. You're just walking straight back to your house.
Mhm.
Okay. So could you write a sentence or two that describes that? Exactly what you said there, walking back from the mailbox, constant rate, something like that.
Okay. Can I start off the sentence saying I'm walking back from my mailbox to my house or something like that? Thank what did we say about the slope, by the way? The slope stays, I forgot what we said, like the same or
Yeah, constant slope would be good. Basically, you're trying to say you're just walking back at the same speed. You're not you're not I don't want to say it. Like you're not like running or you don't stop to talk to anyone.
yeah. I only run back to my house if I'm checking the mailbox. If I'm only gonna run back if it's with my dog because I gotta let him have his energy get drained. He's energetic. He's a crazy little guy. Here's what I wrote.
Okay, so we're missing some words that the instructor would want to see, like the graph is an example of, and you want to try to avoid using first person, of walking back from the mailbox to the house. I mean, you could be first person. Um, the slope stays the same by walking the same speed from the mailbox to the house. You might add in some words here like the following. Uh, which is about 100 meters away from the house back to the house. Distance, a number could be helpful. Okay, so let me actually put this in the chat because you're going to want to use this for the next one here. So in this next graph, it kind of looks like the first one. If you just focus in on this portion here on the left, but then it goes down below. So if your house is here, the mailbox is here, what happens if you keep going? Like you're walking, down the sidewalk, you see your house, but then what are you doing here?
Maybe like I saw someone, one of my friends in the neighborhood, and want to go talk to them.
Yeah, maybe walk to a friend's house. So you can describe basically the same scenario up here, except you would say I walk to a friend's house, but the friend's house is much further away. Like they're kind of like double or triple the distance away in the other direction. So you have to say something like that. Friend's house, other direction, further away.
Mm. So now you want me to write that?
Yes.
Sorry, that was I don't know if you heard that, but that's
Good morning, ladies and gentlemen.
that's
This is
the
Ivana from Art Auctioneer,
announcements.
inviting you to the under $500 and more art auctioning.
That announcement scared me. Anyway, sorry.
Okay.
I did not expect that. So you want me to write about how the slope changed because I went to my friend's house, basically.
Not this so the slope change. You're just talking about the distance.
All right.
Yes. You can reuse a lot of what you have, starting at the mailbox, friend's house.
I'm almost done writing.
Okay.
All right, here's what I wrote.
Right, so just like the previous one, you got to try to avoid as much first person as you can. You want to say the graph is an example of something like that. That's less first persony. Uh, you could say starting at the mailbox and walking back home, um, but continuing past home towards a friend's house the other direction. And you want to add in here that it's much further away than the mailbox. Right. So the reason is like the height here is not as the height, not the same as the height there.
Mm-hmm.
Okay. All right. Good job. So next thing here is to make these graphs, which I think should make a little bit um more sense here. So let's talk about, I don't know how this is going to work here. Let me make some room here. Insert this one. You'll probably want to you send as a document. So the biker travels away. So the biker's starting at the house, and then they travel for half an hour. Okay, call that 30 minutes. And then they just rest. They do nothing for 10 minutes. And then they come back home. So we'll say 60 here, 60 or 20 minutes later, they come back home. Something like that. So this is the position versus time. Is that okay?
Yeah.
They go away and then they stay and then they come back. So these endpoints represent like home. Okay, now the distance graph is a little bit different. Um, I run out of room. Okay, so the distance graph, let me do that down here. So the first part of the position and distance graph looks exactly the same. They're going for 30 minutes, and then their distance doesn't change for the next 10 minutes. But then the difference is here, they have more distance for the next 20 minutes because the distance the person is riding their bicycle increases, even though they're coming back to home. So the main difference between these two graphs is that in position, you're coming back home, but in distance, like you keep going. Your distance increases as you're riding your bicycle, even if you're coming back home.
Right.
Okay. That's just to help move it along here. Go work. Okay. A car travels 50 meters east in 15 seconds, what is the car's average velocity? So velocity is distance divided by time. So what was their distance? What was their time?
Okay, their distance was 50 meters and their time was 15 seconds.
Okay. So when you divide those, what is the result of that?
Um, I don't know. Like, wait, 15 you want me to do 15 divided by 50, right?
Yeah.
Okay, that's gonna be 3.33.
Okay. All right. So we can say 3.33 meters per second. All right. So question number 8, a motorcyclist starts from a standstill. In 15 seconds, it reaches a velocity of 20 meters per second. What is the motorcyclist's average acceleration? Oh, we actually do need to make a change to the previous one. I apologize. Well, maybe. Okay, so average acceleration, it's just written poorly, is velocity final minus velocity initial over time. So in this example here, um, the velocity final is the 20 meters per second. But what is the initial velocity if you start from rest or from a standstill? What is your velocity if you're at a standstill?
0, right?
Yes. So it's 20 minus 0 over 15.
Okay. So that's gonna be, what's 20 divided by 15 is 1.33. Wait, sorry, not 1.3, 3.3, no, sorry, 1.33 is right. I'm sorry. I keep, I, I did that right, I think.
3.33. This time it's
No, no, no.
meters per.
It's 1.33. Sorry, I
Sorry,
got that.
yeah. 1.33 meters per second squared. Okay. All right. Okay, question 9. During the U.S. trials for the 2004 Summer Olympics, Michael Phelps broke his own world record in the 400-meter individual medley when he clocked at 4 minutes and 0.841 seconds. What was his average velocity and his average speed? Okay, so velocity is, in this case, distance over time. The time you're going to have to convert to seconds. So what is 4 minutes plus 0.0841? Sorry, 0.0841 seconds. What is that in just seconds? How do you convert minutes to seconds?
How to convert minutes into seconds? I don't remember.
So how many seconds are in a minute?
Oh, 60 seconds. So yeah,
Okay, so how many seconds are in?
like 240 seconds.
Okay,
But I think that's right.
okay, so it's 248.41. Okay. Now there's this whole discussion of difference between velocity and speed. Often these formulas are used interchangeably, but they're actually wrong. Velocity is displacement over time. So in the case of Michael Phelps or any swimmer, does he start and end at the same place or not?
He does end at the same place.
So his displacement is 0, which is 0 meters per second. But the distance is 400 meters.
All right,
Could
let's do
you
like a
yeah, could you
lot of
calculate
math.
that for us, please?
All right. So for the distance and time, the answer is gonna be 1.61.
Okay, that works.
Yeah. And then for the displacement and time, that's gonna be 0.
Yeah, the displacement is 0 because he started where he ended, basically.
Yeah.
Any questions, thoughts on that?
No, I'm good.
That's interesting. All right.
What's interesting?
Oh, just this Zoom thing. There's a Zoom thing that I don't understand, but that's okay. I know way too much about Zoom. They should pay me to help them figure out their bugs. Um, all right. So got some more questions here. It's a pretty, like, you'll see this again in physics. A lot of physics students struggle with this. Um, it's like hard math. So, okay, sitting in the passenger seat, you observe that the drive of the car needs only 3 seconds to come from a speed of 35 miles per hour on the entrance ramp on the interstate to a speed of 70 miles per hour on the interstate. What is the car's acceleration? So the acceleration is the change in velocity, which is the final velocity minus the initial velocity over time. So what is the final and the initial uh, speeds or velocities in this case when you're accelerating to get on the interstate?
Let's see. Velocity. This says 70. It says there's 30 seconds, 35 miles per hour. I guess what they're wanting us to do is to add the time together and figure out what
Nope,
to go from there.
nope,
I don't know.
nope. I'm just asking what's the final velocity or speed and the initial velocity and speed from that first sentence there.
70 miles per hour.
Okay, and what's the initial?
There 3 seconds.
Nope,
Sorry,
35.
35.
Okay, now one of the problems here is that that's in miles per hour, and the time is in seconds. So we need to convert seconds to hours, or we have to convert uh these units 35 and 70 to miles per second. Um, it doesn't really matter, but it's kind of a pain here. So I would convert seconds. So 3 seconds, there are in 1 minute, 60 seconds, and in 1 hour, there are 60 minutes. So this ends up being 3 divided by 3,600, which is 1 over 1,200 uh, hours, which isn't very much. I mean, that's the whole point.
Wowie.
Yeah. So the next thing here is that when you divide it by time, the time is 1 over 1,200.
Mm-hmm.
Right, so try to do this calculation for us, please. You may want to use the Desmos scientific calculator.
Okay. I mean, in this, I'm gonna use Desmos. It's
Okay,
time. I haven't used Desmos in a while. Scientific. Okay, the answer for that is it says like 42,000. All right, what's next? Also, are you talking because I think you're muted again?
yeah, sorry about that. Yeah, so that's correct. And then we got to do this part here. Uh, we may have to convert this to a different unit. So could you do a quick internet search to see the acceleration of some sports cars? Drop that in the chat.
All right.
And make sure you give me a link for that.
Alright. Trying to find I'm trying to find one right now. If Wikipedia's providing me with something.
Yeah, like maybe you
I
can
got
look up your dream car. Let's see what the acceleration of that would be.
right now I don't have a dream car. All I know is in the future I just want a BMW. I just don't know the model of a BMW that I want.
Well, look up a BMW sports car and you should be able to find its acceleration or search for that.
It says it takes like 3 seconds for a BMW to accelerate.
So that's not acceleration, that's just time. We want the acceleration value.
Okay. From what I'm looking at, it says that it went from 0 to 60 miles per hour in like 3 seconds, but that's time. We just want the acceleration.
Uh,
I can't find anything. No.
okay, so kind of a workaround for that is if you can go 60 miles per hour, that's and I'll just put this in the chat here. 60 miles per hour in 3 seconds equates to 26.82 meters per second divided by 3 gives you gives you 8.94 meters per second squared. And that's much higher than this. Okay. And what I would do is get a link for something like that so we can put it in here. And then we want to write a sentence that says how do these compare? And basically you're going to say that the sports cars are faster than this. But could you give me a link to what you found there?
Yeah,
Maybe
sure.
maybe not a Wikipedia link, but something else.
Here's the link. The link.
So copy link. All right. So basically, you want to tell me in your own words that the BMW accelerates faster than the car that you're in the situation. So give me one sentence for that, please.
How did these compare?
Well, the
Mm,
BMW, this is the BMW,
yeah,
and then this is the scenario and the problems. So which is faster?
I think the BMW.
Yes. So give me a
For my sentence, can I say that the BMW is faster because it has a higher miles per hour rate than the scenario?
We're just talking about acceleration. You just gotta say the acceleration of the BMW is greater than scenario in this problem. Right, do you have that sentence? There we go.
Yeah, I just wrote it.
Okay. All right, very good. So we are going to stop there for today. Let me go ahead and stop the recording. All right, I'll see you next week.